Perfect. Well, hey, everyone, thank you guys for coming. I really appreciate it. And EBSA, thank you guys for having me. It's always great to work with you guys and be educating people. So today I'll be talking about combustible dust testing specifically. And if you guys have any questions, whether they be in English or Spanish, please let us know. We're here to help and educate. So just a little bit about myself. So I am a sales engineer with CV Technology, and CV Technology designs, manufactures, and sells explosion protection equipment for processes handling combustible dust. I am based out of Jupiter, Florida at our headquarters, but I cover Mexico and the Rocky Mountain region of the United States. I graduated from the University of Florida with an aerospace engineering degree, and I love traveling, scuba, and hiking. And there's a picture of me at Teotihuacan. I was just down in Mexico City about 2 weeks ago. So before I really get into the specific testing that can be accomplished with dust, I would like to kind of ease into that conversation with just starting off with the basics of what a dust explosion actually is. So a big industry example here is going to be the example of a log. So if you take a log and you try to set it on fire, it's going to be very hard to set on fire at first, but then it's going to burn for a very long time. But if you chop that log into smaller pieces, it's going to be easier to ignite and it's going to burn for less time. And the same thing goes for dust. If you chop that kindling into very fine particles, it's going to burn very fast and it is going to be very easy to ignite. And that's because you have more surface area of that dust reacting directly with the oxygen. And the big point of this is whether it's 30 minutes or 30 milliseconds, the same amount of energy is being released from that log or that log that's chopped up into dust. So you're releasing that energy in a smaller amount of time, causing more energy to be released. And just to go over real quick, there are 5 main elements of a dust explosion. The first thing we're going to start off with is the fire triangle. So you're going to need a fuel, and that is going to react with oxygen. And then to start that reaction off, you're going to need an ignition source. Common ignition sources in a facility will either be a spark, a hot surface, maybe coming off of a dryer or some other kind of equipment that is adding energy, or a flame. And when you disperse that dust into the air or suspend it in the air, you allow for a flash fire. And that allows for that dust fire to propagate much faster through your process. And then where the last element of the dust explosion pentagon is going to be confinement. And that's going to be putting that flash fire in an enclosed vessel. And that allows for pressure to build inside of that vessel and cause a catastrophic explosion. These are the kinds of explosions that you see on the news, the very deadly and dangerous ones. And another quick review is going to be NFPA. So NFPA 660 is the fundamental document for combustible dusts. This is essentially our playbook and how we design all of our systems, and it tells owners and operators of facilities what to manage and how to manage your combustible dust. So there are 4 main steps in doing this. The first one's going to be determine the combustibility and explosibility of the materials, which is what we're going to focus on today. So that would be dust testing or using published values for those materials. And then once you determine that, you're going to identify and assess the specific risks for your facility. So if you're handling a dust collector or a filter receiver, and if you're handling that dust in there, you have to take steps to mitigate it. And that kind of leads me to the next point, is managing that. So that's either adding explosion protection, specific electrical enclosures, or anything else that is going to manage that risk of the explosion or fire. And then the last step there is going to be communicate. So this is telling all of your plant personnel the risks and making sure they're aware of the risks of the facility. And again, today we're going to specifically focus on determining combustibility and explosibility, and we'll kind of go through all of the different tests that can be completed to determine that. So a little introduction to explosibility of particular solids. So combustible dust is a little bit different than a flammable gas or a flammable vapor. And this is because dusts come in all varieties of sizes, shapes, and have different moisture contents, whereas a gas is normally a homogeneous mixture, so it's really all the same. You're working with the same gas in plant A and the same gas in plant B. Those are going to have very similar values for explosibility, whereas with a combustible dust, you can have different sizes of materials, and moisture content play a big factor in determining how dangerous that dust is. And over here on the left-hand side, let me get a pointer out. So these are different samples of wood dust. So as you can see, all of the particles are different size and shape. And depending on that shape and size is what's really going to determine how dangerous that material is. And this also is affected by what kind of process you're running. If you're pulling very fine dust collection particles, it is going to be much more dangerous than a large chunk of dust. And what do we mean by dust when I'm talking about it? NFPA classifies a dust as any material less than 500 microns. Anything larger than 500 microns still has the ability to explode or combust. However, for the purpose of this conversation, we'll be talking about material under 500 microns. And going back to my point about particle size, so particle size is probably the #1 factor when it comes to determining how dangerous a dust is. And that's because of the surface area of that particle. When you have more surface area within able to react with that oxygen faster, your dust is much more easy to ignite, and it provides a much more energetic explosion. So this is a good example of granulated versus powdered sugar. So they're the same material. However, granulated sugar is a much lower risk because it settles in the air. So imagine you have a big chunk of dust and you throw it in the air. That granulated sugar is going to come down a lot faster than the powdered sugar because it is heavier and is more dense at that time. And here's a good example of that. So this is for redwood sawdust shavings, and this is a test we recently completed, so I thought it was a really good example to show you guys here. So if we only sieve that material and use particle reduction, and we don't mess at all with the moisture content, it actually turned out to be an explosible concentration. However, if we only take those wood chips and we dry those to 12% moisture content, it was deemed non-explosible. But if we dried it to 12% moisture content and sieved it, it was determined as explosible, and it actually came back with KST and Pmax values, which are explosibility values that we'll talk about a little farther down the road. And then per protocol, per the ASTM, American Society of Testing and Materials protocol, we grind this down to less than 75 microns, and we dry it to less than 5% moisture content. And as you can tell, the KST and Pmax values, which are the two most fundamental values when determining your hazards of your dust, changed drastically. Typical KST values range from 0 up to 400, where Pmax can range anywhere from 2 bar to 12 bar. And NFPA allows us to make a determination on how we want to test our materials or determine what your explosibility values are. So they're The first step would be industry published values. So NFPA, and there's multiple other sources, have published data on common materials. So think sugar, flour, wood. Most common materials have a published value, or you can take the step of dust testing of your specific material. Another important point I really want to make is the absence of previous incidents cannot be used as a basis for deeming a particulate as non-explosive. Plants can go 50 years without an explosion. However, one catastrophic explosion can wipe an entire plant out. So you don't want to use that absence of previous incidents as a way of saying, I don't need to protect my process. And here are 3 really good resources for that published explosibility data that I was talking about in the beginning. So NFPA 660 in the annex section of it has published data for most common substances. There's also a book called Dust Explosions in Process Industries by Rolf Eckhoff that also provides this data. And then the one on the right here is going to be Justice, which is a German database. And they were the original database for KST and PMAX explosibility values for dust testing. And so just to go through the advantages and disadvantages of the published explosibility data. So it's going to be quick because you're going to be able to pull that data right off of a published site, whether that be 660 or Justice. And it might save you money on explosibility testing. However, this isn't too big of a factor. Explosibility testing is relatively low cost when compared to explosion mitigation equipment. And it also gives a conservative result. And this is because what I was mentioning earlier with particle size and moisture content really determines how dangerous your dust is. So if they published data with a high moisture content and a very large particle size, it might not be applicable to your process. And that kind of leads me into the disadvantages, is it may lead to an underprediction of risk because of that particle size and moisture content that I was just talking about. And it may lead, but it could also lead to an overprediction of risk, meaning that your process has higher moisture content and larger particle size than what was actually published in NFPA or Justice. And today we'll really be focusing on option 2 of that, where you can actually determine the explosibility with these tests. So the first step of this flow chart that I'm showing right here is going to be to collect your dust sample and then prepare that sample to be shipped off to a lab and be tested. So the first step you have to do is create a sampling plan, and you want to try to figure out where you're actually going to try to protect against this dust. So you don't want to grab dust from a dust collector over here when you're actually trying to protect this dust collector. Again, those could have different particle sizes and moisture contents, and those could affect how dangerous the dust is, directly affecting what kind of explosion mitigation system that an explosion vendor will provide. And then it's also important to use descriptive sample names. So if you just label it sample 178-Z45, you're really not going to know what that dust is. You want a more descriptive name like starch mixture from baghouse 1, for example. You want to know exactly where this dust came from when you go to protect it. And right here's a little flow chart. So the first thing is sample collection. How are you going to do that? Are you pulling it from a dust collector? Are you pulling it from the ground? It all determines on where you are adding explosion protection equipment and what you're trying to protect against. And then you always want to secure this in a airtight and watertight bag, because moisture content has a big effect on dust testing. And you're going to ship that to the lab. They're going to run it through a moisture analyzer to tell you how much moisture content is within that dust. And then we also have the option to grind that sample. And grinding that sample can provide a result that can work for all of the different bag houses because it gives you a much finer particle size. And two other steps to keep in mind here are going to be as received or per protocol. And these are two different ways that this dust can be tested. So as received is exactly how it sounds like. It's as the material was sent to us. If you put it in this bag, we're going to test it exactly like that. Per American Society of Testing and Materials protocol, we're going to dry that sample and we're going to sieve that sample to less than 75 microns. And this is going to give you a very conservative worst case result. And this worst case result can be used across your process as long as nothing else in your process is lower than that 5% moisture content and having less than 75 microns, which 95% of the time it is not. And then moving down the list here, we're going to go to KST and PMAX testing. So down this way. And the first thing is you're going to determine whether your sample is explosible or not. And essentially what this is typically done in is a 20-liter Koellner sphere over here. And this is a metal sphere that has an air compressor at the bottom where you put your dust sample, and it is going to kick that dust up into the air, and it is going to send two igniters on both sides that spark and try to ignite that dust. And whether you have a go, which means the dust is explosible, or a no-go, which means it's not explosible, determines your next course of action. And we'll kind of just jump right into the go here. So if it is a go, we're going to try to figure out how dangerous that dust is now. Now that we know it is explosible, we're going to determine the Pmax and KST values. So these are dust-specific material properties of your dust. And Pmax is exactly like it sounds. It's the maximum pressure that can develop in a contained explosion of that dust, whereas KST is going to be how fast that dust reaches that level or that pressure limit. And typically for these tests, we need about 2 pounds of dust. And here is a chart, and the main chart I really want to focus here is the one on the bottom right here. So this is dust concentration and pressure, change in pressure here. So the big thing to keep in mind here is there is a specific concentration of dust that will yield the highest pressure inside of your vessel and the largest explosion. So if you have too much dust in your system, it won't explode, or it would be a weaker explosion. Whereas if you have too little dust, it will also do the same thing. And what do these values actually mean? It really means how dangerous your dust is, how big is the boom if this dust were to combust. And these two values, KST and Pmax, are the most important values when designing an explosion protection system. This is because these values determine how large your vent area is or your suppression system. And if any of you guys have any other questions on explosion protection, I'd be happy to answer them. Not the focus of today's presentation, but so on. One other thing I want to mention is that some dust, and typically in the agricultural industry, for example, most dusts are in this ST1 category. So KST values between 1 and 200, and that's determined as a weak explosion per NFPA. But the main gist here is these are still explosible and these are still dangerous dust. They just don't explode as quickly as some of these higher KST dusts. And I'll skip this slide for now. So moving down the line, now that we're determined how dangerous the dust is, we're now going to look at the explosibility limits. So the limiting energy required to start that explosion, the minimum ignition temperature, so the minimum temperature that's going to cause an explosion, as well as explosive concentrations, so how much dust you need at that specific limit to cause an explosion. So both of these tests, minimum explosive concentration and limiting oxygen concentration, are both typically done in the 20-liter Kohler sphere that I was talking about, or the more rare 1 cubic meter sphere. Both of them can be accomplished in either of those. So minimum explosive concentration is really useful in situations where dust concentrations are low and can be controlled. So sometimes high efficiency cyclones do not operate above the minimum explosive concentration, meaning that you will never have the amount of dust present in that cyclone to cause an explosion. So this is a very important test if you're running specific equipment where you can control your dust concentration here. And typically for this test, we need about 1 pound of dust. And limiting oxygen concentration. So this is useful in situations where oxygen can be controlled. We typically see this in the pharmacy industry because most of their dusts are very dangerous, very high KST and Pmax values. However, limiting your oxygen concentration is often very expensive. And then jumping into the next one is going to be ignitability, so minimum ignition energy. So think of a static spark. If you grabbed the door handle and had a static discharge, this is to measure how much discharge can set your dust on fire. And this is very important when you have low MIE dusts. So dusts with very low minimum ignition energies can be easily sparked and the explosion can start. So it's very important to determine what that threshold is when you're determining bonding and grounding of all of your equipment in your facility. And just to get into a little bit more, so this is a guideline from one of our dust hazard analysis reports on what a facility should be doing when they're handling a specific powder. So a very low powder should have extreme sensitivity, and this is bonding and grounding of everything. Personnel should be away from the area, and moving higher and higher, you have less requirements on what kind of bonding, grounding, any kind of electrostatic discharges should be released. And then temperature is also another important thing to keep in mind. So if you have a dryer per se, or any kind of other equipment adding temperature into your process, it's very important to know what that limit is for that dust to start to combust or explode. And there's two different tests here. So there's a minimum ignition temperature in a cloud. So this is, think of a dust collector when you have that dust suspended in air, and then the minimum ignition temperature in a layer. Think of dust sitting on the top of a pipe in the process. And the minimum ignition temperature for a layer is typically lower than in the cloud because you have more material sitting there that has the ability to start a fire or combust. And one last test that I want to go over is going to be the burn rate test. So you have explosibility on one side, meaning that that dust has the ability to explode. And then you have combustibility, which means that dust is able to set a fire. And when that dust has the ability to explode, we typically don't do this test because we know that dust has the ability to be on fire. However, a dust can set ablaze or burn, even if it is not explosible. And this burn rate test essentially starts with a torch on one side, and you're going to light the beginning of the sample and see if the sample has the ability to continue that chemical reaction and burn down the line here through the process. And if it does, you have to take fire protection standards into account and look at fire protection. And this test normally requires about 2 pounds of material. Yeah, that's all I really got. So at CV Technology, we have the capabilities to analyze and do the dust testing. We also have the capabilities to consult and help you guys through dust hazard analysis, which is another very important point that I want to bring up. In NFPA, a dust hazard analysis is now required, and this is going to be an in-depth review of your process to determine where your hazards exist, what strategies you have in mitigating those hazards, and what strategies you need to mitigate the rest of the hazards that have not already been mitigated already. And then we also provide explosion mitigation equipment. Yeah, so it's really a full circle, and I'm here to answer any questions you guys have. Feel free to reach out to EBSA directly or me, and we'd be happy to help you guys out.